Okay, hello. We're going to go over the second part of this week's homework, which was about the second derivative test and curve sketching. Okay, let's go. So 33 is relatively straightforward polynomial. It says f of x equals x cubed minus 3x squared plus 3. That's the problem. And the task is find all relative extrema. Well, this is a task that we got good at last week, and the way we did it is to find the derivative and see where the derivative changes sign. But this is an alternative method. So we take the derivative, we get 3x squared minus 6x, and we still factor it, so far it's just the same, 3x, x minus 2, and now that's that. So okay, at this point it's tempting to just not use the second derivative test because frankly speaking the simplest thing to do at this point, in my opinion, would be to use the first derivative test, which is to say make a sign chart, and we have 0 and we have 2, and we see that this is a quadratic with leading coefficients positive, so it's going to be plus minus plus, and therefore we will have a relative, the derivative is positive, goes from positive to negative, so that means that the function is increasing then decreasing, so there's a relative max at x equals 0, and then the function goes from decreasing to increasing at x equals 2, and so there's a relative min at x equals 2, and we're done. Honestly, that's what I would do here. But let's just say you felt like, for some kind of reason, using the second derivative test. Well, you can. What is the second derivative test? The second derivative test says you still have to do all this work of finding, you still have to do all the work of finding the critical points. So in other words, we still have to take the derivative, and we still have to factor the derivative and observe where the derivative is 0. But instead of making a sign chart, now instead you just take the second derivative. Okay, that feels like more work, but you know, polynomials, the more you differentiate, the easier it gets. And so differentiating again using this version gives me 6x minus 6. And, yeah, there it is. And so now I simply plug in 0. And when I plug in 0 into the second derivative, I get negative 6, which is negative. And what do I conclude from that? There is this picture. I'll sort of go slowly this time. The picture is, when I plug in 0 I get 3. That's a fact. But also, 0 is a critical number. Specifically, 0 is a number that when I plug into the first derivative gives me 0. So if the first derivative is 0 at x equals 0, then that means that there is a horizontal tangent line at x equals 0. And, okay, while I'm at it, I'll just plug in 2, because it's the other number I care about. If I plug in 2, I get 8 minus 12 is negative 4, and 3 is negative 1. So, okay, so when you plug in 2, you get negative 1. And it's also the case that there is a horizontal tangent line at x equals 2. And, okay, so now what information do I get from seeing that the second derivative is negative? Well, if the second derivative is negative, then that means that the function is concave down. So the second derivative negative, function concave down, hands down, tangent lines lie below the curve, and that means that my function, locally speaking, looks like this. And since we know, especially based on the way that we did it, which is I think the good way, that the definition of concave down is that tangent lines lie above the curve, down, down, then we know specifically that there's this horizontal tangent line, and if this horizontal tangent line lies above the curve, then that's just another way of saying that the curve is never bigger than this horizontal tangent line, which is another way of saying that this curve is never bigger, at least locally, than the line y equals 3. And if the curve is never bigger than this horizontal line y equals 3, then in fact we've proven that there's a relative max here at x equals 0. Okay, that's the logic of it, so we can sort of conclude that if the first derivative is 0 somewhere, like at 0, and the second derivative is negative, which it is, then we conclude that f has a relative max at x equals 0. And to do the other one, if we plug in 2, now we get 12 minus 6 is 6, which is positive. And what does it mean if the second derivative is positive? Well, we proved as a theorem that if the second derivative is positive, that means the function is concave up, hands up in the air. If this function is concave up, here, again, going through the logic kind of slowly, it means, based on our definition of concave up, that tangent lines lie below the curve, and specifically this line y equals -1 lies below this curve everywhere, and so this curve is never less than y equals -1, and so y equals -1, and so that means that there's a relative min there. And so from the fact that the second derivative is positive at x equals 2, we conclude that f has a relative min at x equals 2. That's really kind of all there is to it. The second derivative test is something you use to find relative extrema. You either use the first derivative test or the second derivative test. You would never use both in a single particular problem. And we could probably just leave it at that. This is not the most important thing in the world, but it is useful in some cases. So I don't know if we need to continue to do these other 3 problems, but we might as well. And actually, I think at least a couple of these problems demonstrate why you might want the second derivative test in your life. So here we go. Take this function, number 42. This is a more complicated function. So this is 2 sine x plus cosine 2x. Okay. And the directions are use the second derivative test to locate all relative extrema. Okay, I think we know how to do this. We take the derivative of this is 2 cosine x, and the derivative of cosine 2x is, well, the derivative of cosine of something is negative sine something back inside 2, so this is going to be minus 2 sine 2x. Okay, so the chain rule is being used, or has been used, but taking the derivative was pretty easy. Now comes the hard part. The hard part is finding the critical numbers where the derivative is 0. Okay, well, I guess we can do that by using the identity for sine 2x. It's 2 sine x cosine x. So that becomes minus 4 sine x cosine x. And now if I factor out a 2 cosine x, then I get 1 minus 2 sine x. So, okay, these problems are all written to work out nicely. Okay, all this work has brought us to this factored form of the derivative, and now we can see when the derivative is 0, and the derivative will be 0 whenever cosine x is 0, and whenever sine x is a half. Yeah. Well, when is on the interval 0? This problem said do it all on the interval from 0 to 2 pi. So when is cosine 0? Well, answer at pi over 2 and 3 pi over 2. And when is sine equal to a half? Answer at pi over 6 and 5 pi over 6. Okay, so I've successfully found all the critical numbers, but I now need to test them all to find out whether there are relative extrema there, and in particular, which kind of relative extrema are at those points. Well, if I was going to use the first derivative test, I have to know precisely when this derivative is positive and when this derivative is negative. In other words, I need to go through that whole complicated mess of drawing the circles and overlapping shaded regions and making a sign chart, and honestly that's not so hard, but it's kind of an advanced pre-calculus technique. Perhaps it would be less work, I don't know if this is true or not, but perhaps it would be less work to simply use the second derivative test. In other words, though I have to do more calculus here, and I'm putting a box around that because I'm going to go back to that version of the first derivative because I think it's the easiest to differentiate from this version. So I have to do more calculus, I have to take another derivative. What is the derivative of 2 cosine x? It's negative 2 sine x. And then this derivative will be, well, it's going to be derivative of sine is cosine, so then there's another chain rule, so it's going to be minus 4 cosine 2x. Hopefully I'm doing this right. Let's see. Derivative cosine negative sine, and then the derivative sine 2x is cosine 2x back inside 2, of course. So now I get this thing. Do I like this? Not so much, but and we can maybe factor out a negative 2, maybe that's a good idea. So we get sine x plus 2 cosine 2x. Okay, so this is my second derivative, and now, supposing, well, let me just keep going. Now supposing I have a question, my question is, okay, what is really going on at pi over 2? So it's maybe a particular critical number that I care about. What is the happening at x equals pi over 2? Is it a relative max or a relative min, or perhaps neither? I can just settle this once and for all by plugging it in to the second derivative. And maybe this is not so bad. Sine of pi over 2 is 1, so we get negative 2 times 1 plus, and that would be cosine pi, which is negative 1, so that's negative 2, so that's negative 1, and so the answer is 2. And that's positive, so that means that there's a horizontal tangent line, but also it's concave up, which means that, that there's a relative min. So f has a relative min at x equals pi over 2. So in some ways it is more work, but it's easier work because I don't have to make that sign chart. This is the power of the second derivative test. Okay, I assigned this problem, so I might as well do it by finishing this off. And now I plug 3 pi over 2 into the second derivative. So I'll put a green box around this formula because I'm going to use it 4 times. So I have now also I want to try f prime of pi over 6, and I want to do f prime of pi over 6, and also f double prime of 5 pi over 6. So yeah, and well, what happens? You get negative 2 times sine of 3 pi over 2 is negative 1. But now 3 over 2 times 2 is 3 pi, cosine 3 pi is negative 1, so that's negative 2. So that's negative 3 times negative 2 is 6, so that's positive. And if the function is concave up, then it means that there's a... did I do that right? Yeah, I guess I did. That seems surprising. No, not surprising. Okay, yeah, so also a relative min. So relative min at 3 pi over 2. And hope I'm not making any mistakes. Now I plug in pi over 6. So sine of pi over 6 is a half. If you multiply this by 2, you get pi over 3. Cosine pi over 3 is also a half. So that's plus 1. So that's 3 halves times negative 2 is negative 3. Oh man. And that is negative. And since the second derivative is negative, that means the function's concave down, and the tangent line lies above the curve. So that means there is going to be a relative max on the original function at x equals pi over 6. And here, last one, I plug in 5 pi over 6, sine of 5 pi over 6 is a half. And cosine 2 times 5 over 6 is 5 pi over 3. Cosine 5 pi over 3 is also 1 half times 2 is 1. So I guess I get the same thing. Somewhere I'm sure I'm making an error here, but perhaps not. And so there's also a relative max at... let's see, just give me 1 second to double check this business. Minus 4%, yeah, factored correctly. These two have the same sign, and they also have the same, yeah, I guess it's fine. Because cosine pi over 3 and cosine 5 pi over 3 both have cosine 1/2. Yeah, okay. So therefore, well, I think we're done talking about that problem. Okay, two more. And 44, I think yeah. In some ways you sort of have to pick hard problems in order to convince yourself that the second derivative test is actually worth doing, because it's worth it only in very specific situations when well, let's see if these two problems exhibit this effect or not. These next two problems, 44 is x ln x. Okay, so here is my function x ln x. Let's just take the derivative. What happens when we do that? We get derivative of the first times the second plus the first times the derivative of the second. And so indeed, this derivative is just ln x plus 1. Okay, and when is ln x, well, what are the critical numbers for ln x plus 1? Well, this will be 0 whenever ln x is -1. You e up both sides, and therefore this happens at e to the -1 or 1 over e. Okay, and now, well, once again, personally, I know enough pre-calculus such that it's not too difficult for me to produce a sign chart for this first derivative, because I know what natural log looks like, and if you move it up 1, then it's just going to be moved up 1, so the magic point will be here, and it's going to look, basically something like that. And I just learned that at 1 over e it crosses. Okay, and so the old way to do this problem would be to apply the first derivative test and to say, okay, ln x plus 1, you're only defined for positive numbers, of course, and by a sort of graphical knowledge about what ln x plus 1 looks like, I conclude that you must be going from negative to positive at x equals 1 over e, and therefore there will be a relative, the function's going from decreasing to increasing, so there's going to be a relative min at x equals 1 over e. But arguably, it would be less work, or maybe just easier, to simply take the derivative again, and if you take the derivative again, what is the derivative of ln x plus 1? It's just 1 over x. So that seems kind of nice, because now if I just plug in 1 over e into the second derivative, I just get 1 over e, and that's e, and that's positive. And since that's positive, then I know that at 1 over e, that I have a horizontal tangent line, but also the function is concave up, so tangent lines lie below the curve, so there's a relative min. So the conclusion of this problem is that there's a relative min at x equals 1 over e, and I guess it's up to you whether it's easier. In this case it was shorter and less thinking to simply take the derivative again and stick in this critical number and see whether it's positive or negative. Okay, really proven our point, I think, but we do one more problem. Number 50, this time no commentary. X e to the negative x is the function. I differentiate once and get Okay, so some chain rule, product rule going on here. Can't help but talking, I guess, but you know, here I just did the product rule combined with the chain rule, and I factored. I see immediately that there's only going to be one critical number when x is 1. I now take the second derivative, which admittedly is more work. So again, the chain rule, the derivative of e to the negative x is e to the negative x back inside negative 1. Now there's a negative here, so I subtract out, and now I need to differentiate x e to the negative x again, which in some ways I kind of already did. And so I get negative e to the negative x minus e to the negative x. Then this negative and this negative cancel, so plus x e to the negative x. And what is that? It's negative 2 e to the negative x plus x e to the negative x. In other words, it's e to the negative x, x minus 2. So that's probably right. And now I can test this critical number x equals 1 by plugging it in to the second derivative. And when I plug 1 into the second derivative, I get something negative. And since it's negative, that means that the function f is concave down. And so if f is concave down, then it means that f has a relative max at x equals 1. Okay, good. Stopping that, and then we'll go on to curve sketching.